So yes, I wanted to share with you today these first results from the ALMAQUEST survey, which is the ALMA MaNGA quenching and star formation survey. So it's even longer when you spell out the entire acronym. So this is a survey that I'm leading with Li Hui Lin at Asia-A. We have a fairly large team, so I point you to the website if you'd like more details. But I particularly wanted to highlight two of our junior scientists on the team, Xian Pan, who is a postdoc at MPIA, soon to be faculty back in her home country of Taiwan, and Mallory Thorpe, who is a PhD student with me here at UVic. So the motivation for the ALMAQUEST survey can really be captured in this schematic cartoon, which shows what we know about the population of galaxies in the local universe. And so we know that star-forming galaxies organize themselves in this so-called main sequence, so a tight correlation between the star formation rate and the total stellar mass, but that there are starburst galaxies that scatter above this relation, and then there are also green valley galaxies that have somewhat lower star formation rates for their stellar mass. And then, of course, the red and dead elliptical galaxies, or the quenched/quiescent population, that can have an order of magnitude or more less star formation. But of course, there is a lot more complexity within galaxies than is captured by this schematic. And we know that we can't just assign a single star formation rate to a given galaxy. And so this has really been demonstrated beautifully in these large IFU galaxy surveys that we've been hearing about earlier this week. So this is a figure from one of my 2018 papers in which we used the MaNGA survey data to look at radial profiles of star formation. And specifically, we split the galaxy population that was observed by MaNGA at that time into bins of their global delta SFR, so how far above or below the main sequence they were in their global star formation rates. And so the, excuse me, the y-axis of this plot, this so-called delta sigma SFR, this is a measurement on the kiloparsec spaxel scales of how much more or less star formation you have in that spaxel compared to what you would expect given how much stellar mass is in that spaxel. So put another way, if this delta sigma SFR is positive, you have more star formation rate, a higher star formation rate than you would expect. So for example, we can look at the purple profile here. So this is for the galaxies whose global star formation rates are highest above the main sequence, so the so-called starburst galaxies. And what we see is that they have elevated star formation rates at all radial distances out to at least 1.5 effective radii. But the enhancement in the star formation is particularly enhanced in the inner regions. And then we can make profiles that step down through the main sequence and out the other side. And so then this red profile here is showing the star formation rates for the passive galaxies. And we can see essentially just a mirror image here of what we see in the starburst population, which is that the star formation rates are suppressed out to the largest radii, but that suppression is strongest in the inner region. And so this and other works has led to this concept of inside-out regulation. We've heard a lot in this conference this week about inside-out quenching, but also that the starbursts are also regulated preferentially from the inner regions. But of course, if we really want to understand star formation, we have to add gas into the picture. And so that has really been the motivation of the ALMAQUEST survey. So we took 46 galaxies from MaNGA and observed them with ALMA in CO 1-0. And so importantly, our ALMA setup allows us to measure the molecular gas on the same spatial scale of around a kiloparsec as the MaNGA galaxies. So because we would like to both probe the mechanisms that both boost and quench star formation, our ALMAQUEST sample is selected to have galaxies that are both firmly on the main sequence, but also those that have got central starbursts, and also some that are in the Green Valley. And over here on the right, I'm just showing you 3 example galaxies from the survey. This is the MaNGA H-alpha intensity map, and then this is the ALMA CO map. So in this talk, I'm going to be focusing on three principal properties, three different surface densities: the surface density of the molecular gas that we get from ALMA, and then the surface densities of the stellar mass and the star formation rate that we get from MaNGA. So you can combine these three surface densities in three different pairwise scaling relations. And so the first one is the very well-known Schmidt-Kennicutt relation. So this is the tight correlation between the star formation rate and the molecular gas. And so this, of course, has been studied for many decades, both on global scales and on subgalactic scales. So this is just the ALMAQUEST view of the Schmidt-Kennicutt relation. So there are some 15,000 spaxels that go into this. Then there is the resolved version of that star-forming main sequence that I mentioned at the beginning of the talk. So the correlation between star formation rate and stellar mass. Now, you don't need ALMA for this. And this has been well studied with tens of thousands of spaxels or hundreds of thousands of spaxels in just the IFU surveys. But nonetheless, this is the ALMAQUEST version of the resolved star-forming main sequence. And then the third way you can combine these variables is to look at how the molecular gas follows the stellar mass. And this hasn't really been looked at very much in the past, so we had to come up with a new name for it. So we've dubbed this the resolved molecular gas main sequence. And so you can see that there's this very nice correlation with a tight scatter between the molecular gas and the stellar mass as well. So given that all three of these variables correlate with one another, giving you these three scaling relations, it won't come as a big surprise to see that you can look at these three variables in three-dimensional space, and that there is this, this nice three-dimensional correlation that's sort of somewhat cylindrical. And so you really get the three individual scaling relations by projecting this three-dimensional structure onto the two-dimensional planes. So in our first ALMAQUEST paper, which was led by Li-Hui Lin, we argued that it's actually the Schmidt-Kennicutt relation and the molecular gas main sequence, the two sort of physically fundamental scaling relations here, and that the star-forming main sequence is just sort of a projection of those other two relations. And so whilst we all love to plot the star-forming main sequence, it's actually just a manifestation of these two other more physical relations. So now we can start to unpack these scaling relations and look at the differences within the given galaxies. So here I'm showing you 28 of the 46 ALMAQUEST galaxies, so one panel per galaxy. The grayscale is the same in every panel. That is the ensemble of all of the star-forming spaxels. That's just there for visual reference. And then the red points are showing you the Schmidt-Kennicutt relations for the individual galaxies. So all I want you to take away from this figure is that whilst there is a Schmidt-Kennicutt relation in each of the galaxies, the normalization and the slope as well is actually somewhat different from galaxy to galaxy. So sometimes it's above the average, sometimes it's below the average. We see the same diversity in the star-forming main sequence. So again, some of these relations are above the average, some are below, and also there are quite different shapes. Sometimes it's somewhat linear, other times it has a turnover at high stellar mass. So again, great diversity from galaxy to galaxy. And then we see the same diversity when we look at the resolved molecular gas main sequence. So then the question is, what is regulating these different scaling relations from galaxy to galaxy? And so we can try to look at how the normalization of these different scaling relations might depend on some global galaxy properties. And so we found a number of possible correlations and anti-correlations. I'm just showing a few here. So for example, we found that both the star-forming main sequence and a resolved Schmidt-Kennicutt relation, their normalization relative to average, which is what's plotted on the y-axis, seems to anti-correlate with the morphology of the galaxy. And the molecular gas main sequence has a correlation with the total, the global specific star formation rate in the galaxy. So the summary from this part of the talk is that these three scaling relations exist, but there is considerable galaxy to galaxy variation. This ties back right to the very first talk of this session in terms of environmental drivers. So up until now, I've been talking about the star-forming spaxels within the ALMAQUEST sample. But one of the main goals of this project is to understand also the quenching mechanisms within galaxies. And so now we can think about studying the scaling relations, not just for the star-forming spaxels, but for the regions in the galaxies where the star formation is shutting down. And in particular, I'm going to refer to retired spaxels or retired regions within the galaxy. These aren't fully quenched yet. They're characterized by very weak H-alpha emission that is typical of a very old evolved stellar population. So here, just as an example, is the molecular gas main sequence for, in blue, the star-forming spaxels that I've already shown you. And now overlaid in the orange contours, you can also see the results for these retired spaxels. So you can see that they have their own molecular gas main sequence, but it's offset from the star-forming population. And specifically, there are low surface densities of molecular gas at a fixed stellar mass in this retired population. And you can see explicitly, thank you, you can see explicitly that this is essentially a difference in the gas fraction by looking at this inset histogram here. So the distribution of the gas fractions in the star-forming spaxels, so gas fraction is just this divided by this, is shown in blue, and then for the retired galaxies in orange. And you can see that there's almost an order of magnitude less gas in these retired regions. So this is indicating to us that this retirement process of star formation is linked to lower gas fractions. Now, not a complete absence of gas, because we actually have quite a high detection fraction for the molecular gas in these retired regions, but certainly less of it. So then the $64,000 question is, what is causing the star formation to shut down? What is leading to this retirement and then presumably ultimately the quenching? And so one of the favorite mechanisms in the extragalactic community is, of course, feedback from an AGN. So we'd like to now be able to look at these scaling relations in galaxies that host AGN, but unfortunately we don't have good statistics for that in ALMAQUEST. So to address that question, we've turned to using a different survey called EDGE-CALIFA. Now, EDGE-CALIFA is very similar in its construction to ALMAQUEST. It has both an IFU survey component, that's CALIFA, and then molecular gas follow-up using KAMA, and that's the EDGE component. So this survey has 126 galaxies in it, and there are a handful of AGN in here that we can use. So here is that molecular gas main sequence once again, but now showing you just the EDGE-CALIFA data. So the blue again, that's star-forming spaxels in EDGE-CALIFA. Orange, that's retired spaxels in EDGE-CALIFA. And you can see once again the gas fraction difference in this completely different sample between the star-forming and the retired spaxels in orange. So again, a deficit. And then now in red, I'm plotting in these individual points the central AGN regions. And there are 5 galaxies that go into this. And you can see that they, again, have this molecular gas main sequence, but again, like the retired spaxels, lower gas fractions. And you can see that again explicitly here. I should emphasize here that the star-forming spaxels I'm showing you here are in the same central radial regions of galaxies. So I'm really comparing central star-forming regions with central AGN regions. We can also look at this within a given galaxy. So here are 4 of the AGN in that EDGE-CALIFA sample. And you can see that even within a given galaxy, the gas fractions are lower in that central AGN region than in the extended star-forming region. Often by just a factor of few, but in this one case, by an order of magnitude. So I think I'm probably almost out of time. So in summary, we have this relatively new survey that combines MaNGA and ALMA data. And I've shown you that we have these 3 scaling relations, but that there is significant diversity from galaxy to galaxy in the way that these scaling relations manifest. And that these are probably due to internal properties, different internal properties of the sample. And then when we look at the retired and the AGN regions of these galaxies, we see lower gas fractions. So maybe this is a smoking gun that AGN can affect the gas fractions in galaxies and might ultimately suppress their star formation. Thank you very much.